picture a traditional power plant control room. You've probably seen them in movies or maybe on a news broadcast during a massive blackout.
Oh, yeah. The walls are just covered in those immense flat screens.
Right, blinking with like thousands of tiny green and red lights. And you have operators hunched over incredibly complex spreadsheets.
And two-dimensional graphs.
Exactly. And they're trying to mentally map a sudden spike in a data feed to a physical transformer that might be, 30 miles away in the freezing rain.
Which is just an immense cognitive load.
Oh, absolutely.
I mean, you're constantly forcing your brain to translate abstract two-dimensional data into reality, like seeing a sudden drop in voltage on a line graph,
Right.
And then having to visualize that in a three-dimensional real-world space.
Yeah.
You're doing all of this while the clock is ticking.
Which is frankly like trying to navigate a dense, unfamiliar city using only a spreadsheet of raw GPS coordinates.
Yes, instead of just, pulling up a map.
Exactly. But today, we're diving into a stack of technical documentation, architecture diagrams, and market analyses that effectively takes that entire room of flat screens and, well, shrinks it down.
It's incredible.
It really is. It turns all that data into a living, three-dimensional physical projection right in front of you. So welcome to your custom deep dive.
Glad to be here for this one.
Our mission today is to decode a fascinating piece of technology called the AI Spatial Interface, or as the documentation calls it, ASI.
Which represents a profound shift in how we interact with critical infrastructure.
It really does.
We are moving from observing data on a screen to essentially literally stepping inside it.
Okay, let's unpack this. We are looking at the absolute future of how we manage smart energy grids.
That we are.
And honestly, reading through these design specs, the ASI solution sounds wildly futuristic, but it's actually built on tools we are already starting to see in the consumer space.
What's fascinating here is that the core concept relies on mixed reality, or MR.
Right, so not just virtual reality where you're totally closed off.
Exactly. Rather than looking at a flat computer monitor, ASI generates a highly detailed 3D scale model of the power grid.
Okay.
And it superimposes it over the real world around the operator. So if you are the operator, it allows you to see, examine, and interact with the virtual grid.
Like it's actually right there in the room with you.
Yes, as if it were a tangible architectural model sitting right on the table in front of you.
That's wild.
And it achieves this by using geolocated data, meaning it accurately maps every virtual power line and substation directly to its real-world geography.
So that transition from staring at a flat screen to physically walking around a 3D model is a massive leap.
It's a total paradigm shift.
But to really understand why this is revolutionary for the energy sector, I think we need to move from the visual concept to how a human being actually interacts with it.
Right, how they solve real problems.
Exactly. And looking at one of the system diagrams provided in our sources, it captures what I call the trifactor of ASI.
Yes, the three main pillars.
Right. It points to AI simulations, 3D spatial visualization, and easy interaction. So it's kind of like Tony Stark's hologram table.
That's a great comparison.
But instead of building an Iron Man suit, you're, keeping the lights on for a whole city.
Exactly. And those three pillars have to work in perfect harmony.
How so?
Well, you have the spatial visualization giving you that realistic tabletop view of the grid. Then you have the AI simulations overlaying theoretical predictive data onto those real-world models.
Okay. That makes sense.
And finally, the interaction layer is what ties the human to the machine.
Right. But I have to push back a bit here on that interaction layer.
Okay.
Because the documentation specifically mentions users navigating and inspecting these grid components using hand gestures.
Yes, natural manipulation.
But is natural hand manipulation actually practical for high-stakes, critical infrastructure?
It's a very valid concern.
Because, when I think of managing a city's power grid during a hurricane, I want precise keystrokes. I want hard physical buttons.
You don't want to be waving your hands in the air.
Exactly. I don't necessarily want an operator hoping the system registers a pinch or a swipe. It sounds, honestly, a bit like a boardroom gimmick.
I get that. Especially for anyone who's ever fought with a touch screen that, just wouldn't respond.
Oh, the worst.
But this goes directly to the heart of that easy interaction pillar.
Yeah.
And it is entirely about human psychology under pressure.
Okay, how so?
Well, the goal isn't to look futuristic. The goal is radically simplifying user engagement to reduce hesitation.
Reduce hesitation, right.
Think about what happens in an emergency. Stress floods the system, adrenaline spikes, and seconds really matter.
Right, you don't have time to second-guess your keystrokes.
Exactly. By superimposing these theoretical AI simulations onto real-world 3D scenarios, the interface closes what designers call the conceptual gap.
Which is that friction between seeing a raw number on a screen and understanding what that number actually means in the physical world.
Precisely. When an operator has to read a 2D line graph, recognize an anomaly, and then mentally translate that to visualize how a power surge will physically cascade.
Through a whole network of suburban substations.
Right. That takes time. It introduces a massive potential for human error.
Because the human brain is doing all the heavy lifting of spatial rendering.
Exactly. But if they can physically see the 3D model glowing red along a specific geographic path, and they can reach out, isolate a malfunctioning node with a physical gesture.
And instantly see the AI simulate the result of that action.
Yes, the entire paradigm shifts.
Which means if a severe winter storm takes out a main line, the operator isn't waiting for a text-based alert.
No, not at all.
Or, like, cross-referencing a manual. They literally see that sector of the hologram go dark.
And their natural human instinct to reach out and fix the physical object takes over.
That's incredible.
It really is. It makes
Okay.
training and split-second decision-making far more effective because it relies on experiential learning.
And our innate human spatial awareness.
Exactly. You aren't calculating probabilities in your head. You are experiencing the data.
You're using your natural instincts to manage the machine rather than forcing the human to think like a spreadsheet.
Beautifully put.
But that brings up a massive technical hurdle. If I am isolating a node with my hand, that hologram has to be perfectly synced with the physical world.
Oh, absolutely. Latency is the enemy here.
Right. If it lags by even a few seconds during a crisis, I might make a catastrophic decision based on old data.
Which would defeat the whole purpose.
Exactly. So how exactly is this interface ingesting that physical data fast enough to prevent the operator from making decisions based on a ghost of the grid?
That brings us to the backbone of the entire operation. The digital twin, or DT.
The digital twin.
Right. The 3D interface incorporates a complete virtual replica of the physical energy grid. And you hit the nail on the head earlier.
About the sync.
Yes, this cannot just be a static 3D map. It is continuously updated with real-time data from sensors all over the actual grid. It gives the operators a complete, up-to-the-millisecond picture of the functioning power network.
So if a tree falls on a power line on the east side of town, the sensors detect the voltage drop.
Instantly.
And the digital twin updates immediately, so the operator sees that line sever in the hologram.
Yes. And to handle that kind of complex, high-volume data flow without lagging or freezing, the developers had to make a very intelligent architectural choice on the back end.
What kind of choice?
Well, in their component layer, they took the API request handler, which is essentially the software messenger that takes the user's requests and fetches the data.
Okay.
And they split it into two distinct parallel parts. You have the grid data service and you have the simulation data service.
Let me make sure I'm following the logic here. If the API is like a waiter in a restaurant taking your order to the kitchen,
I like this analogy.
you don't want the same waiter pouring water and also trying to cook a complex 5-course meal.
Right.
You separate the tasks so nothing drops.
That is a perfect analogy. The grid data service is the waiter pouring the water.
Handling the basics.
Exactly. It handles requests related to grid configuration. The static layout, where the physical transformers are geographically located, the basic topology of the network.
It's essential, but it's relatively stable data.
Right. While the simulation data service is the chef cooking the 5-course meal in real time.
The heavy lifter.
Precisely. The simulation data service is processing the heavy dynamic computations.
Okay. Like what?
It connects the back end to run complex power grid simulations and retrieve predicted outcomes. We're talking about calculating grid stability metrics.
Oh, wow.
Dynamic load balancing as thousands of homes turn on their air conditioners at the exact same time, and predicting power generation from renewable sources like wind or solar.
So separating those data streams ensures the spatial interface remains fluid and responsive to the user's hand gestures.
Exactly. Even when the backend is running intense, heavy AI predictions about what might happen 10 minutes from now.
Here's where it gets really interesting, though. Because as I was combing through these architecture diagrams, looking at how the API splits the grid data from the simulation data, I noticed another component quietly sitting in the background.
Ah, you spotted the evaluation component.
I did. which the documentation sometimes refers to as the BS, or baseline system.
Right, the baseline system.
And it turns out this entire setup isn't just monitoring the power grid, it's monitoring the operator.
Yes, it is.
The documentation notes that this baseline system includes the systematic evaluation of implicit and explicit metrics about the user.
It's a crucial part of the design.
But why does a power grid tool need to gather psychological or behavioral metrics on the person using it?
Well, if we connect this to the bigger picture, you have to remember that this technology, while incredibly promising, is still actively being validated.
Right, it's not fully mainstream yet.
Exactly. This specific iteration of ASI was developed in the scope of a European project called the HumAIne Energy Pilot. Specifically, pilot number 5, partnering with an energy organization called UBI.
HumAIne Pilot 5. Okay.
Right. When you introduce a completely novel, paradigm-shifting HMI, a human-machine interface, into a high-stress environment, you can't just assume it works better because it looks cooler.
Good point.
You have to empirically prove that it reduces cognitive load.
So the baseline system is tracking how the user interacts with the holograms to make sure the holograms aren't actually making the job harder.
Exactly. This cross-platform evaluation component gathers continuous data about user interaction.
To assess user-friendliness and, UI friction.
Yes. It's the critical engine for the validation trials of the human-machine interface.
What kind of metrics are we talking about here? If I'm the operator, is it tracking how fast I move my hands or where my eyes are looking?
It evaluates a range of interactions. By processing user metrics collected during controlled simulation scenarios, the developers can see exactly where an operator hesitates before making a gesture.
Yeah, that's smart.
Or where a specific physical movement is misunderstood by the sensors. Or even where the sheer volume of visual data in the 3D space might actually be overwhelming the user, causing them to freeze.
Which is fascinating because it's tackling a massive problem in traditional control rooms. Alarm fatigue.
Yes, alarm fatigue is a huge issue.
Because if 100 red lights flash on a 2D screen at once, the human brain just shuts down.
It gets overwhelmed.
Right. And they want to make sure the 3D environment doesn't just recreate that same overwhelm in 3 dimensions.
Precisely. Ensuring the interface actually improves an operator's ability to keep the grid stable is just as critical as the accuracy of the grid data itself.
Because if the tool is clumsy, the grid goes down anyway.
Exactly. And that data directly informs the iterative design process. They can tweak the interface.
Like maybe make a critical warning glow a different color?
Sure. Or require a simpler hand gesture for an emergency shutoff.
Right.
All based on how real human bodies react under simulated stress.
That makes total sense, and it proves they are taking the human element seriously.
Very seriously.
But a brilliant, thoroughly tested piece of technology only matters if it actually survives the open market.
That is the ultimate test.
Which brings us to a massive commercial hurdle. This ASI technology was developed within this very specific HumAIne energy pilot context.
Right.
But if you've ever worked in enterprise procurement, you know the uphill battle ASI is facing here.
Oh, it's a steep climb.
How does a relatively new, specialized tool plan to compete against established, multi-billion-dollar industry titans?
Well, the market for industrial modernization in Industry 4.0 is incredibly crowded.
Dear.
And organizations are notoriously risk-averse when it comes to buying new software.
Right, and looking at the extensive competitive market table provided in our sources, I have to play devil's advocate for a moment.
But it's here.
If I'm a chief technology officer at a major energy grid, I have massive enterprise competitors knocking on my door. Siemens Accelerator, GE Digital Twin.
ABB ability, EcoStructure.
Exactly. Heavy hitters. And on the other side, I have the massive tech platforms offering the visual rendering, Unreal Engine, Unity Industrial.
HoloLens 2, Vuforia, Magic Leap.
Right. So why would my boss approve a highly specialized spatial interface when the old corporate adage says nobody ever gets fired for buying Siemens?
That's a fair question.
What is ASI's actual unique selling proposition to break through that kind of institutional inertia?
ASI has a very specific, synthesized market positioning that bypasses that exact problem. Let's break down that list you just read, using a wardrobe analogy.
Okay, I love a good analogy.
Tools like Siemens Accelerator or GE Digital Twin, they are fantastic. But they are essentially the generic one-size-fits-all winter coats of the industrial world.
One size fits all.
They have the digital twin tech, the predictive maintenance, the analytics. But they are broad.
Meaning they aren't specialized for energy grids.
Exactly. They are built for factories, logistics, and energy all at once.
Yeah.
Meaning they are largely still tied to traditional 2D interfaces or have very rudimentary mixed reality capabilities.
Okay, I follow that. But what about Unity or Unreal Engine? They are the absolute kings of 3D rendering and MR Why wouldn't an energy company just use them?
Because Unity and Unreal are development platforms, not ready-to-use solutions.
Ah, I see.
To use our analogy, they are selling you the raw fabric and the sewing machine.
So you have to make the coat yourself.
Exactly. They offer incredible high-fidelity simulations, but they require an energy company to hire a massive team of specialized developers to build the power grid application from scratch in-house.
Which takes years and millions of dollars.
Right. And then you have the hardware solutions like HoloLens 2 or Magic Leap.
Which are just the physical classes.
Exactly. They are heavily hardware dependent and have very limited pre-built software applications specifically tuned for the nuances of the energy sector.
Ah, I see. So ASI is essentially selling a bespoke, tailored suit.
Beautifully said.
Sure, a company could buy raw fabric from Unreal Engine and stitch it themselves, or buy a bulky generic coat from Siemens, but ASI is giving them something ready to wear.
Meticulously tailored specifically for the energy grid.
That's a great pitch.
That's exactly their unique selling proposition. It's a hybrid MR and AI focus built specifically for the energy industry from the ground up.
It combines that hyper-specific 3D spatial visualization with natural manipulation.
An immersive training that an energy operator actually needs without the massive in-house development overhead.
But bespoke suits are incredibly expensive.
Usually, yes.
How are they actually selling it to these risk-averse organizations? Because big enterprise software usually comes with a massive, prohibitive upfront price tag that scares off smaller grids.
Well, they've strategically opted for a software as a service, or SaaS, core model.
Okay, a subscription model.
Right. This allows organizations to host the ASI solution entirely in the cloud, which significantly lowers the barrier to entry regarding server hardware.
Makes sense.
But the real key to their business plan is custom pricing and adaptive licensing.
Meaning they don't charge a rural electric cooperative the same multi-million-dollar fee they would charge a national energy conglomerate?
Precisely. This adaptive licensing makes the technology accessible to giant multinational energy companies, but crucially also to smaller renewable energy startups, municipal grids, or even university research centers.
And to overcome that initial hesitation you mentioned, I imagine they have a lot of support.
Oh yes, they provide exhaustive supporting documentation, setup guides, tutorials, video walkthroughs to make onboarding as painless as possible.
And what's their actual route to market? How do they get this tailored suit in front of the people holding the corporate credit cards?
The short-term exploitation plan is highly targeted. They aren't buying billboards.
Right.
They are starting with the production of a highly polished video demonstration to showcase the product's key functionalities.
Essentially showing people what that intuitive holographic interaction looks like in action.
Exactly. Then they're taking that demo directly to sector-specific energy conferences.
They want to engage directly with the key decision makers, the structural engineers, the regional managers, the distribution companies.
Yes. They're giving presentations and showcasing the validated success stories and metrics from their HumAIne pilot programs.
Proving that the baseline system tracked the users and the users performed better.
Show, don't tell.
Right. Don't hand an engineer a white paper. Let them see the hologram respond to the grid.
Exactly. And long-term, as they gain a foothold, they plan to build an online community around the software.
Oh, that's smart.
They want to offer deep educational content and form strategic partnerships with industry leaders to prove the real-world value and return on investment over time.
We've explored the visual interface, the back-end architecture, elegantly splitting those data streams, and the surgical business plan designed to infiltrate the energy sector.
This is a very comprehensive strategy.
It is. But looking at the final sections of this documentation, it strongly hints that the smart energy grid is just the starting line for ASI.
If we connect this to the bigger picture, this raises an important question about the fundamental scalability of spatial computing. While the primary target customers right now are energy grid operators and renewable energy companies, because the pilots successfully validated the interface in that specific context,
Right.
their midterm and future goals are vastly broader.
Where are they heading next? Because if this works for electricity, it should theoretically work for any network.
Right, that's exactly their thesis. They want to expand this spatial technology to other critical, sprawling infrastructure sectors.
Like what?
The documentation specifically names communications networks, road networks, and rail networks.
Wow. So instead of just seeing tower lines glowing in your living room, you could pull up the geographic traffic of massive fiber optic cables across an entire continent,
Yes.
or monitor the real-time flow and bottlenecks of every freight train across a national rail system.
That's the vision. The core strength of ASI isn't strictly about managing electricity.
It's about the data.
Right. It's the immersive, intuitive human interaction with wildly complex, spatially distributed data. That strength is universally applicable.
Whether you are balancing the electrical load of a major metropolitan area,
Or rerouting vital internet traffic during a massive server outage.
or managing the logistics of a multi-state highway system during an evacuation.
Exactly. The ability to close that conceptual gap, to see the sprawling network in true 3D and manipulate it naturally, it's invaluable.
So what does this all mean for you listening to this right now? We started this deep dive talking about the sheer cognitive overload of the traditional control room,
Right. Operators staring at flat screens.
forcing their brains to translate endless rows of spreadsheets into a physical reality while emergencies unfold.
A very stressful reality.
But as this AI spatial interface technology matures and expands from the energy grid to our highways, our railways, and the invisible web of our communications, the very nature of how we manage human infrastructure is fundamentally changing
It's moving away from abstract observation and data translation.
and moving toward intuitive, physical interaction. Which leaves us with something fascinating to ponder. If we are rapidly approaching a reality where we can hold the complex arteries of entire cities, power grids, and transit networks in the palms of our hands, manipulating them with the sweep of a hand,
It really makes you wonder.
will the future of infrastructure management feel less like rigid mathematical engineering and more like we are physically sculpting a living organism right in front of us?